Good morning, everyone. I'd just like to say thank you for attending today's course. My name is Ash, and I'd just like to start off by, could we just try raising hands on Zoom just to confirm that we can all hear me at the moment? Great, thank you very much, everyone. I can see the hands are going up, so that's a good sign. So you can all hear my dual tones today. In today's course, we're going to be going through the DSE Four Steps to Synchronising. With me today is my colleague David O'Connor. David, would you like to introduce yourself?
David O'Connor. I'll be answering your questions today. So as the course goes on, please feel free to add anything that needs clarifying, and anything that doesn't get answered, we can always run through some questions at the end. I'll hand it back over to Ash.
Thank you for that, Dave. Yeah, so the plan for today then is we're going to be doing the DSE Four Steps to Synchronising course. What I'd like people to do, please feel free at any point during the course, if you have any questions about what's being presented or any questions related to what's being presented, please feel free to ask those via the question and answer section of Zoom. We will not be looking at the Zoom webinar chat. We will only be looking at the question and answer section of Zoom. So please ask any questions you have via the question and answer. What Dave will try to do is he'll try to answer those questions going forward or going through the presentation. At the same time, I'll be taking regular breaks throughout the presentation to either answer the questions directly or going through some of the questions that have been asked, just to kind of reiterate them for everybody else. We aim to have this presentation go on for around 2 hours, depending on the level of questions. It might be a little bit more, it might be a little bit less, but 2 hours is a good estimate for how long the course is going to be. Okay, right, so we'll begin. So the first thing I want to go over is what the actual aims and objectives are of today's training course. So the first objective is we need to understand what the DSE Four Steps to Synchronising actually are. And we'll be going through that as part of the presentation. We then also need to understand why it's important we do these 4 steps. What's the reason behind it? We also need to understand when do we actually perform the 4 steps to synchronizing. And finally, we need to know how do we do the 4 steps. So to start off with, I'll just quickly go through a summary of what the DSE 4 steps to synchronizing actually are. So the first of the 4 steps is what we call control, basically making sure that the DeepSea module has good control over the governor and AVR. The second step is to make sure that the DeepSea module is correctly monitoring the current that the generator produces, basically making sure power readings, things like that are all correct. The third step is to make sure that all the modules are communicating correctly on something that we call the MSC link. The MSC link is a digital communications link between all of the controllers. And finally, we need to do some phase checks across the generator's switchgear to make sure that there hasn't been any strange wiring problems. It's worthwhile noting that to do the 4 steps, you will need some form of laptop or PC and the DSE configuration suite to perform them. The 4 steps to synchronizing is also used for both commissioning and fault finding as well. I'll go in detail later about each of the 4 steps, but I just first wanted to introduce what they were to you. So now we know what the 4 steps are. We need to know why is it important to do the 4 steps. And for that, we first need to go through a few things. So first we need to talk about what synchronizing is and how synchronizing between generators is actually achieved. Synchronizing to deep sea means three things. The first of which is frequency control. Frequency control is done by controlling the engine's governing system. This could either be an ECU or an electronic governor. So as you can see on the slide, on the left here, we have an electronic governor such as a GAC, Heinzmann, etc. Or we could have an ECU fitted to the engine. In terms of the synchroscope on the deep sea module, this is affecting the frequency, this value here. The job of the governor controls the fueling to the engine to increase or decrease speed. And as speed and frequency are directly related to one another, changing engine speed changes frequency. The next part of synchronizing is controlling the voltage. The voltage is controlled by something called the AVR, automatic voltage regulator, inside the alternator. Again, there are many different AVRs out there. There are some examples on the slides for you to see, but effectively it's controlling the voltage of the generator, which is shown on the synchroscope here. The way the AVR works, it changes the excitation current to the alternator, which in turn changes the voltage. And finally, for synchronizing, we need to worry about something called phase. Phase is measured in degree of difference between one supply and another. So just because two supplies have the same voltage and frequency does not mean they are in sync. You also need to make sure they are at the same phase, effectively have both waveforms lying on top of each other. Now, the way in which we change the phase of a generator is we slightly increase its frequency. So for example, the generator you're synchronizing to might be at 50 Hertz, and the generator that is doing the synchronizing might be at 50.1 Hertz. So as the phase control is done by slightly changing the generator's frequency, this means we must be using the governor again, because we are changing frequency to affect phase. So again, phase control is done by using a governor such as this GAC here on the left, the engine's ECU in the middle, and on the synchroscope, the phase is shown by the dot that appears on the screen. The problem is, though, there are many, many different types of governors and AVRs out there on the market, and also many different types of ECUs as well. So sometimes it can be quite difficult to understand what governor or what AVR is going to be suitable for synchronizing. As a general rule of thumb, for most governors and AVRs, if it has some form of input known as a remote bias input, remote control input, effectively an input in which you can connect a potentiometer, a variable resistor to, then this will allow you to do synchronizing. However, when we talk about electronic engines, such as ones with ECUs, normally these don't have an input for a variable resistor or something similar. But that's not normally a problem, because with most electronic engines, we'll be using CAN bus messages to do the speed control. And those CAN bus messages are normally in the form of something called the TSC1 or DLN1 message. Now, for the sake of this presentation, we're going to be assuming that in most cases, we're going to be wiring into a governor's or AVR's remote bias input, effectively the input on the governor or AVR that uses a potentiometer or a variable resistor. But the principles I'm going to discuss through this presentation are exactly the same if you're using the hardwired signal or a CAN bus signal. So we'll start by looking at a very traditional governor or AVR and have a look at the wiring. So very typically on a governor or AVR, it will have 3 terminals on it, as can be seen on the slide on the left-hand side here. And these 3 terminals is where you would normally connect a variable resistor, a potentiometer. Some governors and some AVRs may have 3 terminals, some may only have 2 terminals. The operating principle between the 3 terminal and 2 terminal governor or AVR, it's exactly the same. So the way that this device works is on one terminal, there is a reference voltage. In this case, it's 4 volts. On another terminal, there is a higher voltage, in this case, 8 volts. And then there'll be another terminal, which is where a varying voltage is applied. In this case, it's in. The way this works, depending on the position of this variable resistor, it varies the voltage to the in terminal. So for example, if we had the potentiometer in its center position, we get 6 volts on the in terminal. If we wound that potentiometer fully clockwise, we'd get 8 volts. And if we wound the potentiometer fully anti-clockwise, we'd get 4 volts. The reason it's 4 volts is because the lowest voltage here is 4. The reason it's 8 volts is because the highest voltage here is 8. And the reason it's 6 volts in the center is because 6 is halfway between 8 and 4. The varying voltage on this in terminal then tells the governor or AVR what voltage or frequency the generator should be ran at. So very typically, most governors will allow plus or minus 3 hertz adjustment, and AVRs will typically allow plus or minus 16% adjustment. These values do change from different governor manufacturers and different AVR manufacturers, but that's just a general rule. Plus or minus 3 hertz for governors, plus or minus 16% for AVRs. So as you can see here, when I apply the center voltage, my generator runs at nominal. And normally this nominal value here is actually set by the voltage trim pot or the frequency trim pot located on the governor itself or the AVR itself. And then depending, as I vary this potentiometer here, it goes up 3 hertz or down 3 hertz around this nominal frequency or voltage as set on the governor or AVR itself. It's also worthwhile noting that I have just used some typical labeling here as plus, in, and minus, but there's no standard for this on different governors or AVRs. You might find it labeled as ABC, T1, T2, T3, XYZ. It could be anything, but normally you'll be able to find this out by looking at the governor or AVR manufacturer's literature, and normally the typical wiring diagram will give you some idea about that. One way to know if your governor or AVR is actually going to work with a deep sea module is if you were to take a DC multimeter and measure the voltage between what would be the minus and the plus terminal. As long as that voltage, as shown here as 4, as long as that voltage is less than 10 volts, it will definitely work with the deep sea unit. Now, anyone who's actually wired up a deep sea controller to a governor or AVR before, they will know that there is no external potentiometer that's there. Instead, you wire the deep sea module directly to the governor or AVR itself. So how does the deep sea module work, and how does that all kind of interlink? Well, if we look at the next slide, in the top left-hand corner, we're actually using the same governor in this example as the previous slide, which happens to be a DYN1 governor, I believe made by Basler, but I could be mistaken by that. So apologies if that's incorrect. You can see we're still using the same terminal designations here. So in, and in this case, plus 4 volts. Just going back a slide, you can see that we have in, and in this case, plus 4 volts as the lowest potential terminal. And these are relating to the terminals on the governor itself, which you can see from the wiring diagram here, is terminal 7, 4 volts, and 9, which is effectively the in terminal, or the wiper of the potentiometer. Again, just going back to the previous slide, you can see that the wiper of the potentiometer is going to the in terminal. So the way the DSE module works in terms of its wiring, as you can see here on the left-hand side, we have no external potentiometer connected. Instead, of the 3 terminals, we're only connecting to 2 of them. This is because the way the DSE module works is it actually generates a voltage across its output. And the voltage we generate then depends on what speed we want that generator to run at. So in this case, if we were to look at the voltage at the terminals of this governor here, it's still the same as it was in the previous slide. 6 volts to run at 50 hertz, 4 volts to run at 47 hertz, 8 volts to run at 53 hertz. That's still exactly the same. Now, the way the DSE module works, however, it then needs to generate a voltage which gets sent to that governor. In this case, for the governor to run at 50 hertz, the DSE module is only generating 2 volts. This is because it's 2 volts added to the 4 volts of this terminal here, which gives 6 volts. And this is actually where the switch 1 value comes in. Switch 1 is actually how many volts or how much voltage does the DSE module need to produce to make the generator run at its nominal frequency. So in this case, we have a switch 1 of 4 to run at 2 volts. We produce 2 volts, gets added to the 4 to make 6 to run at 50 hertz. Again, just going back to the previous slide, you can see the voltages here are still the same, 4, 6, and 8, as we previously discussed. 4, 6, and 8. The only difference is this time, rather than using the potentiometer to generate the additional voltage, we're using the DSE module. And then you can see, if we want to increase or decrease speed, the DSE module adds or subtracts more voltage. In this case, we have a switch 2 setting of 3 plus or minus 2 volts. So for the DSE module to ask the generator to run at 53 hertz in this example, what the DSE module will do, it will go to 4 volts, which is actually switch 1, 2 volts, plus switch 2, 2 volts. And if we wanted it to run at 47 hertz, we'd actually ask the DSE module to produce 0 volts, which in this case is switch 1, again 2 volts, but this time minus switch 2, 2 volts. Now, I know that's quite a lot of explanation I've just gone through, and for some people that might make perfect sense, and for other people that might be a bit too much information. But this is actually not something you guys will have to necessarily worry about. As you'll see as we go through the presentation and go through how we actually set up the switch 1 and switch 2 values, we do not at all use a multimeter. The only reason why I'm going through this little bit of explanation now is just to give you guys some additional information as to how exactly the DSE module is controlling the governor or AVR. And I mainly do this just so that you guys will have a better idea of how to fault find if something goes wrong. For example, now you guys know that the DeepSea module is actually generating a DC voltage on its output. You might have a better idea how to fault find. For example, if you see 2 volts here on the DeepSea module's output, then in theory, you should see 2 volts across these 2 terminals on the governor or AVR. And that can help with fault finding, etc. So I know I've mentioned here as well about switch 1 and switch 2. Switch 1 and switch 2, again, we'll cover more in more detail as we go through the presentation. But just to show you where those are, they're not actual physical switches on the DeepSea module. They're actually sliders in PC software. Effectively, the best way to think about it, as I tried to kind of allude earlier, switch 1 is the center command, or how much voltage does the DeepSea module need to produce to make the governor or AVR run at nominal frequency or voltage. And switch 2 is just how much voltage does the DeepSea module need to add or subtract from the switch 1 setting to make it run at minimum or maximum speed. At this point, I'll just go over to David just to see if we've got any questions coming in by the question and answer section. David, have we got any good questions coming in so far?
We do have one. How long may the wiring be between the station and the gate governor and AVR? And does voltage drop play a role? Effectively, you're only governed by the amount of voltage that you require. As an example, if you require the 4 volts for nominal and 8 volts to run at maximum RPM, then as long as you can adjust your slider to achieve that, then it shouldn't be an issue. So if the DeepSea module has to produce the full 10 volts to allow you to gain 8 volts at the other end of the wiring, then it shouldn't be a problem. Can I also note that can we be adding the questions and answers in the questions and answers section, please, instead of in the chat, because I almost missed that one.
Thank you for that, Dave. Yeah, I'd just like to add a couple of extra points to that as well, because it is a very good question that's been asked, and it is something that occasionally we do get asked at DeepSea. Now, what David said is completely correct. Yep, you know, you can adjust the switch 1 or switch 2 values to compensate for voltage drop across a cable. However, in all honesty, the amount of voltage drop you would get should be very, very, very small. The reason for that is most voltage signals carry very, very small amounts of current, and it's current down a cable that creates voltage drop. So if you're ever wanting to kind of calculate what the maximum voltage drop you might see across a governor or AVR control cable would be using DeepSea module, if you were to make the assumption that the maximum current you would see coming out of the DeepSea module's output was 20 milliamps, you could then, knowing the resistance of the cable that you have used, work out what the voltage drop, because voltage drop is just current times resistance. I've told you that the maximum current would be 20 milliamps. You could then measure the resistance of the cable and therefore work out what the voltage drop across that cable would be. And in most cases, as resistance of cable is very small, and the maximum current that the DeepSea module would ever produce out of its governor or AVR output is 20 milliamps, also very small, then the voltage drop you would see across that cable should, in theory, be very small. Now, obviously, there's ways in which you can emit that by using larger diameter cable, for example, because a larger diameter cable has a smaller resistance. So if you are concerned about long cable runs, the best way to mitigate any sort of voltage drop, which should be small anyway, would be to use a larger diameter cable. I think, though, what is more important, which is a point I did forget to mention on the slide, if I just go back a couple of slides, you will see on the wiring here that we do advise that the cable be a shielded cable between the governor and the deep sea, or the AVR and the deep sea module. This is just because any form of external magnetic interference, even if it's, for example, in the millivolt range, could cause disturbances with some governors and some AVRs, depending on how sensitive their input is. It doesn't have to be anything specially rated like CAN bus cable or anything like that, just high quality screened cable, maybe even the type you use for a magnetic pickup sensor, for example. That would be fine. I can also see that another question has just come in. I'll read this out so everyone can see it. The question is, my generator does not have an ECU. However, the frequency is 53.5 Hertz, and it does have an AVR. I guess I need to look at the AVR to adjust. I'm not sure if the terminal's on the AVR. If not, can you advise what to do? Well, it seems there might be a couple of things on that question, so I'll try to answer them as I can. Firstly, frequency is down to the engine governor, not the AVR. So if your engine is running at 53 Hertz, the first thing you should do whenever setting up a generator, without the deep sea module connected in any way, shape or form, you do need to make sure that the generator runs at 50 Hertz, if that's your nominal frequency, and then adjust the AVR to whatever the nominal voltage should be. So again, just to make it clear, frequency is controlled by the governor, not the AVR. The AVR controls voltage. Similarly though, if your generator is not running at the correct voltage, you will need to make adjustments on the AVR itself to run at the correct voltage. If I just go back a couple of slides to earlier in the presentation, I'll show you some of these potentiometers I'm referring to. The GAC governor is actually quite a good one. If we were to look at this GAC governor here, the potentiometer terminals that the deep sea module would connect into are these ones here, G, H, and J. And under these grommets, which are used for IP isolation, so stop water ingress, there will be some additional on-circuit potentiometers, which, as you can see here, set the nominal speed or nominal frequency of the generator. So normally what you would do with the deep sea module disconnected, you would adjust the onboard potentiometers to make the governor run the generator at nominal frequency, and also adjust on the AVR its same potentiometer for nominal voltage. I hope that answers the question. Okay, so we'll carry on now, and then we'll come back to questions later on. So as you can see, it's very important for synchronizing we have good control over the governor and AVR, because we use the governor and AVR, as I said earlier, for frequency, voltage, and phase control. However, once we've done synchronizing, what happens next? Well, normally the reason why we are synchronizing multiple generators together is so that we can load share with multiple generators. Load sharing is basically just making sure that multiple generators can share the load between them. And the way the deep sea module does load sharing is it doesn't necessarily share the load equally between the generators, because if you have different sized generators, what the deep sea module will try to do is make sure that each generator is producing the same percentage of power. So for example, imagine you had a 100 kilowatt load and you had two generators. One was 200 kilowatts and one was 100 kilowatts. The way this would work is the 200 kilowatt generator would produce 66 kilowatts and the 100 kilowatt generator would produce 33 kilowatts. But the net result is that both generators would be producing 33% of their size. So again, when load sharing, what the deep sea module tries to do is make sure that the generators are producing the same percentage of power, not necessarily the same amount of power. Now, the way in which the DeepSea module does this is we actually have two different types of power we need to control when doing load sharing. The first type of power is something called active power, which most people will know as kilowatts. Now, the DeepSea module measures the kilowatts the generator is producing by using voltage sensing and the current transformers, which you wire into the DeepSea module. The DSE module then knows how much kilowatts that generator has to produce due to the MSC-link communication between the generators. And then the way the DeepSea module controls how much kilowatts the generator needs to produce is by using the engine's governor. So you can see that again, the engine governor is coming into play here. So we actually use the engine governor for both frequency control, phase control, and also kilowatt control. The same can be said for the other type of power that the DeepSea module needs to share. This is called reactive power, mostly known as AVRs. The way the DeepSea module measures AVRs is by using voltage sensing and current transformers, just like with kilowatts. It knows how much kVAR the generator needs to produce because of the MSC link, again, just like with kilowatts. The only difference here is the way the DeepSea module controls kVAR is by varying the control to the AVR. If the AVR varies excitation current, it will actually vary the amount of kVARs the generator produces. So it's very important that the DeepSea module has good control. So just to summarize what we've gone through so far, the engine governor is used by the DeepSea module to control frequency and phase while synchronizing, but it's also used to control kilowatts whilst in parallel with another generator. We use the alternator's AVR for voltage control while synchronizing, but we also use it for reactive power control whilst in parallel with another electrical source. We use the voltage and current measurement of the DeepSea module to measure how much active power, kilowatts, and reactive power, kVAR, the generator is producing. And we also use the MSC link to instruct each generator how much power to produce in terms of kilowatts and kVARs. So you can see there, it's very important that the DeepSea module has good control over the governor and AVR. And it has very good measurement of voltage and current, and also has very good communication. If at any point any of these was to fail or not be set up or calibrated correctly, you will end up having load sharing problems, synchronizing problems, etc. So it is very, very important to do this. So I guess then the question becomes, how do we know how to check that all of these different aspects are working? That's actually where the DSE Four Steps to Synchronising comes into play. And just to kind of go over again what those DSE Four Steps to Synchronising actually are, step one is to check the control of the governor and AVR, because we need to make sure we've got good governor control and good AVR control to make sure that we have good synchronizing control and load sharing control in terms of kilowatts and kVARs, voltage and frequency. The next step is to check the metering to make sure that we can measure the current and power on the CTs correctly, because if they're incorrect, all of our power measurement will be wrong, and therefore load sharing will be wrong. We also need to make sure communications is working correctly, so make sure that MSC link is working correct. Because if the MSC link is not working, the modules will not be able to communicate to one another. And finally, we also need to do phase checks across the switchgear to make sure nothing has gone wrong. So before we go in depth into each of these 4 steps, I'd just like to pass back to Dave just to see if we've got any questions that have come in.
Yes, we've had one gentleman ask what percentage of generate. Sorry, hang on a second. What allowable AVR analog percentage when the generator is running? We're effectively aiming for 75 to 85% when setting up switch 2, but Ash will be covering this shortly. Another gentleman's asked, does the percentage of KVAR have to be equal? When synchronizing, yes, the percentage of KVAR is shared equally across the sets, assuming they're the same size, but it's the percentage that is equal.
Okay, thank you for that, Dave. So yeah, just to kind of go over some of the things that Dave's also mentioned there as well. So we'll talk a bit more about this as we go through the presentation, as Dave said. And normally when we're doing the setup of switch 1, switch 2, which is what we're actually going to be covering next, we're looking for a governor and AVR drive percentage of around 75 to 85%. But normally in most load sharing applications, the governor and AVR percentage should be less than 10%. I'll cover this a little bit more later on as we go through. So we'll carry on the presentation. So we're going to go through now step 1. And step 1 is control. Now, each of the steps we have, they actually have their own kind of mini steps within them, little procedures that we need to do. So in terms of the control, we actually have 4 things we need to do. Setting of the switch 1 for the governor, setting of the switch 1 for the AVR, setting of the switch 2 for the governor, and setting of the switch 2 for the AVR. We need to make sure that we always do the governor first when doing the switch 1 and switch 2 setup procedure. The reason we always do the governor first is generator frequency can affect voltage. However, generator voltage does not affect frequency. So this is why in the procedure you'll see I've always started with doing switch 1 for the governor first, or switch 2 for the governor first. So we'll go through how we set switch 1 for the governor and AVR first, and then we'll go on to how we set switch 2 for the governor and AVR. The way I've done this, I've actually recorded a video which will play, and I shall narrate over that video as we go through. Just because obviously I didn't want to do this live with the generator running in the background, and unfortunately you guys not being able to hear me. So we'll start first with switch 1 for the governor and the AVR. So the first thing we always advise you do when connecting to any DSE module is read this module's configuration. The reason we always strongly advise that you read the module's configuration is that if you do make any mistakes or problems whilst doing this procedure or anything with a DSE module, reading and saving will at least then give you the option to revert back if something has gone wrong at a later date. So you can see here, all I'm going to be doing first is reading the module's configuration, and once done, saving that. And you can save the configuration by going to the top left-hand corner of the software and pressing the save button. Where you choose to save this file, what you choose to name the file, in all honesty, it doesn't matter. We always advise reading and saving before you do anything else, just so that then if something goes wrong, you have a way of reverting back later on. Now, the first thing we need to check in the configuration is to find out what the generator's nominal voltage and nominal frequency should be. Now, we can do this by going to the generator section of the configuration and then going to generator frequency. Here we can see what the nominal frequency should be, and here we can see what the nominal voltage should be. I'll be doing all of this today in phase to neutral. There's no problem doing it phase to phase. As part of the 4 steps, we'll also be connecting to the SCADA section, as you can see here. Just click on the bar, it will open. And we'll be starting and stopping the generator using the mimic section of SCADA, but there's nothing wrong with using the physical buttons on the module. We'll also be looking at the switch 1 and switch 2 settings, which are found under the generator governor AVR interface, as you can see here. So the first thing we're going to be doing is actually setting switch 1 of the governor. And the way we do that, we start the generator, and it's very important you leave the generator breaker open. As you can see here, it's not being requested to close. We then go to the switch 1 slider of the governor, and we then start to adjust. By default, the values will be at 0. And all you need to do is just keep increasing that switch 1 value until you attain whatever your nominal frequency is. In this example, 50 Hertz. You can see on the example here, I've made a lot of change and nothing's happened. This could be due to how the governor works, could also be due to a wiring problem. What we advise you do is keep going all the way to the end until you see a change. Like, for example, I've seen now. It is very important to note, however, in this example, that as I increase switch 1, the frequency is going down. Normally, as you increase switch 1, the frequency would go up. Now, this is not necessarily a problem, and I'll tell you how we combat this problem later, because I want to show you what would happen if we don't fix it to start with. Once we've got the switch 1 of the governor correct, we then start adjusting switch 1 of the AVR. In this example, the nominal voltage is going to be 240 volts phase to neutral, or 415 phase to phase. So we adjust the switch 1 of the governor first to get nominal frequency, then we adjust the switch 1 of the AVR to get nominal voltage. And in this case, you'll see as I increase switch 1 of the AVR, the voltage is actually going up. So different to how the governor works. So now you can see I've reached nominal voltage and nominal frequency by adjusting the switch 1 value. And all I do now is stop the generator. And that's actually how you set switch 1. It's very, very simple. All you've got to do is start the generator, leave the breaker open, and then adjust the switch 1 value for the governor first until you get to 50 Hertz or whatever your nominal frequency is, and then adjust switch 1 of the AVR until you get to nominal voltage, whatever that nominal voltage may be. Again, paying very close attention. If you increase switch 1 and the frequency or voltage goes down, pay attention to that. I'll show you in the next video what happens if we don't fix that problem, and then also what to do if you do see that. So I'll just go back to Dave quickly. Dave, do we have any questions so far on the switch 1 setup?
We've had a few people requesting for the videos and the slideshows. Whoever would like those, if you'd send me an email into support, we should be able to provide them from there.
Okay, we'll carry on then and start looking at how we do the switch 2 for the governor instead. So the switch 2 setup procedure is slightly different. So what we're going to do this time, before we even start the generator, we're going to go into the module's configuration, and we're going to change the nominal frequency. Now we're going to increase it by 2.5 Hertz. So in my example, that would be 52.5. And then we're going to write that to the controller. What we're going to do this time is we're going to start the generator, and as it runs with the breaker open, it will still run at 50 Hertz. When we close the generator's breaker, you will then see that the DSE module will start to try to adjust to 52 Hertz. So we're going to start, and you'll see that when I'm running with the genset breaker open, the the generator is still going to be running at 50 Hertz. As you can see here, still running at 50, not a problem. Then what we're going to do, we're now going to close the generator breaker, and what should happen, we should see the frequency start to increase. However, in this case, you can see the frequency for some reason has decreased. Now, this has happened because as we increase switch 1, the frequency decreased. Now, what a lot of people would do here is go and change the wires around on the back of the DSE module, but that's not the correct thing to do. What you need to do is go to the generator synchronizing sync options and tick the option output reversed as I've shown here. So what's going to happen now, this is the only thing we've changed, is the tick box for output reversed. We're going to start the generator, and if we close the breaker this time, you'll see that the frequency will, instead of going down, now go up. This is what you should always do in this instance. Never swap the wires around on the back of the DSE module. Now, one thing we do get asked quite a bit is, when I tick that box, what actually should happen with switch 1? You'll see with the video, even though I've ticked the box output reversed, as I increase the switch 1 value, the frequency still decreases, and that is correct. That tick box for output reversed only affects switch 2. It has no effect on switch 1. So this time you'll see, as I close the generator breaker, rather than the frequency decreasing, the frequency has now started to increase, just as we expect. Now, we're expecting it to get to 52.5 Hertz, but you'll see it's stuck at 51 Hertz. This is because the switch 2 value is too small. All we need to do now is keep increasing switch 2 until we get to 52.5 Hertz with a governor analog percentage of 80%. You'll see as you keep increasing switch 2, eventually the governor analog percentage will go from 100% and start decreasing. Now, in this example, I've accidentally overshot the 80%. That's not a problem. To combat this issue, I just decrease the switch 2 value. So keep in mind, increasing switch 2 decreases the governor percentage, decreasing switch 2 increases the governor percentage. So I just keep increasing switch 2, decreasing switch 2 until I get 80%. You may not get exactly 80, that's fine, as long as it's somewhere between 75 and 85%, which I've got here. So all I'm going to do now, open the genset breaker and stop the generator. I'm now going to do the exact same test, but instead of going up 2.5 Hertz, I'm actually going to go down 2.5 Hertz. In this case, that would be 47.5. And I'm going to write that back into the controller. So the procedure we're going to do this time is exactly the same. We're going to start the generator with the breaker open. It's still going to run at 50 Hertz. And then when I close the genset breaker, rather than going up to 52.5 Hertz, it's going to come down to 47.5 Hertz. And then we should still see a governor output percentage of somewhere roughly between 75 and 85%. So here I am starting the generator. And remember, you can only request the DSE module to close the generator breaker when the LED underneath the generator button turns on, like so. Generator is now on load. And if we go to the governor and AVR section, you'll see the frequency has started to come down. And eventually, when it gets to 47.5 Hertz, that governor analog percentage should be somewhere between 75 and 85%. As we can see in this example, it's about 84%, perfectly fine. So all I'll need to do now is go back to the Mimic page, tell the genset breaker to open, and stop the generator. But one thing many people forget to do at this point, which is extremely important, is to go back into the module's configuration and remember to change that nominal frequency back to 50 Hertz. Because every time now that we want this generator to run and close the breaker, we want it to run at 50 Hertz. If you don't make that change, every time you close the breaker, it will run at the wrong frequency. So always remember, go back, change the nominal frequency to whatever that is, in my example, 50. And that is how we set the switch 2 for the governor. Now, some of you may be wondering, why do we use 52.5 Hertz in our test? The reason we use 52.5 Hertz, or should I say up and down 2.5, but mainly 52.5 Hertz, is because from a lot of testing we did many years ago at DeepSea, we found that on some engines, as a general rule, the throttle position of a generator running at 52.5 Hertz at no load is roughly the same as a generator's throttle position running at 50 Hertz at full load. So in theory, by us enabling you to prove you can drive up and down up and down to 52.5 Hertz, you've effectively proved you can drive a generator at 50 Hertz at full load. And the reason why we use only 80% of the available range of the switch 2 to do this is just to give you a bit of leeway, if you like, because as I said, the rule we've created is only a general rule. It's not always correct. So before we go on to do the switch 2 for the AVR, I'll just revert back to Dave. Dave, do we have any questions coming in that are worthwhile going over?
Yes, with one person asking, how do I interface with my AVR? That is the same way as governor. You would connect into wherever your potentiometer would be, connecting to reference and signal in. One gentleman is asking, do we have a DSE module with an inbuilt AVR? No, unfortunately not, but we do manufacture a range of AVRs. Another gentleman's asking, why does my generator go into reverse power? That is because you have either not enough or no governor control.
Okay, thank you for that, Dave. So just going back, I did actually see that the question was, do we do we have some DeepSea modules with an inbuilt AVR-I? I believe what the customer there is referring to is what the COMAP module has, which is an external AVR interface for isolation purposes. The good news is yes, all DeepSea synchronizing units, the governor and AVR terminals are isolated. The governor is isolated up to 1000 volts and the AVR is isolated up to 3000 volts. So there is absolutely no need to have any form of external interface between the DeepSea module's governor or AVR output to the respective governor or AVR for isolation purposes, because we have it all built in. And to kind of cover again reverse power, reverse power is basically, it is an issue with the engine's governor, and normally by doing these 4 steps you will find the problem. There are lots of things that can cause reverse power, but we'll cover that more towards the end of this presentation. I can already see as well, there's another question coming about, I'm guessing the customer is asking, does the DeepSea module in this setup procedure, is it wired to the generator's breaker? And yes, a part of this setup procedure, we are asking you to open and close the generator's breaker, because this step, whilst it's meant to be setting up the DeepSea module's control over the governor and AVR, we are not just testing the governor and AVR, we're testing other things. So this, us asking you to prove the governor and the DeepSea module can open and close the breaker is just another test. We'll carry on with the presentation now. So what we're going to look at now is how do we set up the switch 2 for the AVR. Now the setup procedure for the switch 2 of the AVR is effectively exactly the same as the governor. The only difference this time, rather than talking frequency, we're talking voltage. So we go to the nominal voltage, and we're going to increase the nominal voltage by 10%. So in my example, that'll be 264. And we're going to write that to the controller. So just like before with the governor setup, we're going to increase the nominal voltage to 264, 10%. We're then going to start the generator with the generator breaker open. The generator would still run at its nominal voltage. Then as soon as we close the generator breaker, you will see that the voltage will start to increase to that new nominal voltage, in my example, 264. So here we are starting the gen. You can see the breaker is open. We then go to the governor and AVR interface, and you can see the nominal voltage is still 240. Once we close the breaker, you'll see this time the voltage has correctly increased. Remembering that as we increase switch 1 of the AVR, the voltage increased, so there's absolutely no need to output reverse on the AVR. But the voltage hasn't gone all the way to 264 because our AVR's switch 2 is too small. So next, we're going to, as you can see on the video, increase the switch 2 value until we get an AVR analog percentage of 80%. You'll end up seeing from this example that we have very different switch 1 and switch 2 values for the governor and AVR. It honestly does not matter what switch 1 and switch 2 values you get. 0 and 3, 6 and 2, 10 and 1. Honestly does not matter. As long as you achieve what we're asking you to achieve, the switch positions, it doesn't matter. So you can see now that we've ended up with quite a high switch 2 value for the AVR. And finally, that AVR analog has started to decrease. We keep increasing that switch 2 value all the way until we get an AVR analog percentage of, again, 80%. Looking for somewhere between 75 and 85%. So as I'm getting closer and closer in this example to the 80%, I'm just slowing my clicks down, as it were, just to make it easier and not overshoot that 80% I'm trying to achieve. So here you can see we've got a very good value of nearly exactly 80%. Very nice. So all I'm going to do now is go back to the Mimic page, open the generator breaker, and stop the generator. And then just like we did with the governor, we're now going to decrease that nominal voltage by 10%. This would be 216 for my application. And write that back to the controller. Just like before, you'll start the generator, it will still run its nominal voltage, in my case, 240 volts. But then as soon as we tell the DSE module to close that genset breaker, the nominal voltage will then start to decrease down to that new nominal setting of 216. And again, we're looking for an AVR output percentage of somewhere between 75 and 85%. Again, remembering that you can only close the generator breaker once the LED underneath the generator symbol has turned on. So we're available, close the breaker, go back to that governor AVR section, and you'll now see that the voltage has started to decrease down to 216, the new setting, and you can see that our AVR analog has resulted somewhere between 75 and 85%. Which is perfect, no problems. So all we're going to do now, again, is tell the generator breaker to open and stop the generator. But again, remembering, very importantly, to go back to the generator voltage section and change the nominal voltage back to what it should be. In our example, 240 volts. At this point, what I like to do after I've written the configuration is just start the generator up again and close the generator breaker. That will then ensure that the generator runs, or should I say, confirms that the generator runs at the correct voltage and frequency, basically proving that you've remembered to reset the nominal voltage and frequency. So here I am starting the generator again, just waiting for that generator to become available. Again, the LED under the button will indicate when that's the case. Close the breaker. And now if we go to the governor and AVR interface section, you can see correct voltages, and also you can see that the governor and AVR analog percentages are very, very small, which is completely correct. So going back to what was asked originally, what sort of values should we expect to see for the governor and AVR analog when running our generator? Normally, you would expect to see at full load no more than 10% on your governor and AVR analog percentage, no more than 10%. However, if you have droop enabled on your governor or AVR, then we would say no more than 30% at full load. As a rule of thumb, if you are seeing more than 50% on your governor and AVR analog drive, something is very wrong. And more likely, the problem is actually caused by having the incorrect switch 1 and switch 2 settings. So one question we do get asked quite a lot at DeepSea is, what happens if I don't perform these steps? Well, the first problem you'll see is unstable load sharing. If you remember back to the earlier slides, the DeepSea module uses the governor and AVR for both synchronizing and load sharing, because it uses the governor to control kilowatts and it uses the AVR to control kVARs. So if we have bad control or no control over the governor and AVR, we will have very bad control over kilowatts and kVARs, potentially leading to things like reverse power, loss of excitation, and as it says there, unstable load sharing. But as we're also using the governor and AVR for synchronizing, if you're having unstable, erratic, or long synchronizing times, this also suggests that you have very bad switch 1 and switch 2 settings, or no control over the governor or AVR itself. So before we go on to the next step, I'd just like to refer back to Dave. Dave, do we have any questions coming in?
Yes, my generator, just a second. How come I can't get the exact result when adjusting the AVR and governor? This is because the slider itself is stepped. You won't have an issue during load sharing because the adjustment is much finer.
I'd just like to add a few points onto that as well. What Dave said is completely correct. Yes, sometimes you won't get exactly 80%, as Dave's mentioned, because of how fine the switch 2 setting is. And that's, again, not a problem. That's why we've said you need to be in that range of 75 to 85%. But sometimes you may come across a problem where, for some reason, you can't even get within the 75 to 85% window. And this can actually be sometimes caused by settings on the governor and AVR itself. So just taking an AVR I know from memory as an example, if you were to look at the Newidge Stanford MX or SX range of AVRs, they do actually have a potentiometer on the AVR known as a trim potentiometer. Now this potentiometer does not set what voltage the generator runs at. Instead, what it does is it sets how sensitive the input on that AVR is. For example, if you set that potentiometer known as trim fully clockwise, it makes the input very unsensitive. Basically, it means that you will have a very, very, very small switch 2 value And sometimes you'll never be able to achieve the 80% we're asking because the input range has been set very, very wide on that AVR. Conversely, if you on that AVR set the trim pot fully anti-clockwise, that actually disables the input on the AVR. So no matter what the DeepSea module's voltage does, the DeepSea module will be generating voltage that will go to the AVR, and the AVR just completely ignores it because effectively the input's disabled. And that would result in you effectively seeing a very, very high percentage all the time because the DeepSea module is trying to make an adjustment and nothing's happening. So sometimes if you're seeing a problem where you are always stuck at a very high percentage or always stuck at a very low percentage, that could be down to settings on the governor or AVR itself. I've just seen another question come in, which is, what is the percentage value that I must put in reverse power? This is not so much related to this course, but a general rule of thumb, 5 to 10% is normal for a diesel engine in reverse power protection. Another question just come in saying, is it possible to achieve this configuration of switch 1 and 2 on the DSE module without a laptop? Currently, unfortunately, no, that is not possible. If you remember earlier, I did say at the start of the presentation, to do the DSE 4 steps, we do strongly advise that you do have a laptop with you because you will need it to do most of these 4 steps procedures. The reason also being is that during these 4 steps, you may come across other problems with module configuration. And unless you have the laptop, you won't be able to fix them. So it's very important that whilst doing commissioning or fault finding, which is effectively the DSE 4 steps of synchronizing, that you do have a laptop with you. Another question has just come in saying, can 2 gensets with different kVA ratings, effectively different kilowatt and kVAR ratings, synchronize and load share using the DeepSea modules? Yes, that's perfectly acceptable. Again, if you remember back to one of the first slides I had, I did mention how the load sharing works with DeepSea. And we do support load sharing of different size gensets because what we do at DeepSea is we do not share the load equally between the generators. What we try to do is make sure that the generators are producing an equal percentage of power based on their own ratings. So for example, each generator would always produce 33%, regardless if one generator was smaller or bigger than the other. Okay, what we'll do is we'll carry on now with the presentation, and we'll come back to questions in just a moment. So the next step is to look at metering. And we'll discuss now what do we mean by metering. So really metering, it's checking that the current transformers are wired correctly to the DeepSea module. So to do this procedure, what we first need to do is make sure that the generator bus is not live and no other generators are connected to it, so their breakers are open. We're then going to start a generator and once available, close the generator onto that bus. And we do then need to apply a purely resistive load around 10% of the generator's size to the bus. Now, ideally, this purely resistive load would come from a load bank. And ideally, the load bank would be a 3-phase load bank as well. Now, the load bank itself does not need to be big. It can be quite a small load bank because in this test, we're not actually load testing the generator or testing its load acceptance or rejection capabilities. We're just making sure that it can measure the kilowatts and current and power correctly. Now, I do appreciate that in a lot of cases, getting a load bank to site, or even during testing and manufacturing, can sometimes be difficult. So one thing you could try doing is maybe renting a single phase load bank to do these tests. It just takes a little bit longer because you'd have to test each phase individually rather than testing all phases at once. Though, in all honesty, it doesn't actually have to be a load bank itself. I've actually done this setup procedure myself without using a load bank by actually making my own load bank using electrical heaters, effectively anything that is purely resistive. So when we're doing the tests, what we're looking for are the following issues. We first need to check that all three phases, when using a purely resistive load bank, are at unity power factor, a power factor of 1. If a power factor of 1 is not displayed across all three phases, that then suggests that some of the CTs are on the wrong phase. So for example, maybe the L1 CT has been wired to L2 and the L2 CT has been wired to L1. If all the power factors are correct, but the kilowatts are being displayed as negative, then this suggests that the orientation of the CT or the S1 and S2 connections of that CT are the wrong way around. So just to help explain this a little bit further, I've got these diagrams and some readings to show what we'd see if everything was correct. So on the right-hand side here, you can see we've got L1, L2, L3, all wired correctly to L1, L2, L3. And all the orientation of these CTs is correct. The load is on this side. We can see everything is wired correctly because the DSE module is showing the correct amount of kilowatts and the same kilowatts across all three phases, and all the power factors are at 1. So in this case, we know that everything is wired correct. However, in the next example, for some reason, the connections have been swapped over on the back of the DSE module. So the L1 CT has been wired to L2, and the L2 CT has been wired to L1. The first thing we need to check here is power factors. So whenever doing the step number 2, the first thing you should always check is to see if the power factors are correct. In this example, even though we are powering a purely resistive load, the same load that was just shown in the previous example, we have incorrect power factors. And this incorrect power factor here is caused by L1 and L2 being swapped over. But in the same vein, you can also see that the kilowatts are being shown incorrectly. So this is why we always we check the power factors, because if the power factors are wrong, this fault here causes 2 issues: incorrect power factors and incorrect kilowatt readings. So we first correct the power factor. If after we've corrected the power factor problem, this issue here, and we still have negative kilowatt readings, this then means S1 and S2 of the CT have been swapped over, or the physical orientation of the CT is wrong. So you can see here, L1 is showing negative kilowatts, when in actual fact, it should be positive kilowatts. You can't always rely on the stickers or the indications or markings on the CT. Many times we have at DSE come across CTs with plastic cases or stickers that are wrong because the iron core and the windings inside have been connected incorrectly. So this test will always prove if the DSE module is measuring kilowatts correctly. So what happens if we don't perform these tests? Well, again, you will end up having unstable load sharing, because just going back to the previous slides, if we look at what was wired correctly, here you can see that we should have 10 kilowatts and no VARs. Looking at the first problem, we supposedly now have 0 kilowatts and 0 VARs. So we're reading power completely incorrectly on this generator. Or in this example, we have 0 VARs, but a lot less kilowatts. So if the DeepSea module cannot measure the power correctly, it will not know how to load share correctly. And if it does not know how to load share correctly, your load sharing is going to be unstable. Another fault that we potentially could end up having here is false reverse power or loss of excitation alarms. Reverse power being excessive negative kilowatts and loss of excitation being excessive negative kVAR. Again, just going to the previous slides, you will see here we have negative kVARs on one phase, even though it should be 0 and negative kilowatts. So it's extremely important that we check the CTs, because if we do not, it is very likely that you'll end up having bad load sharing and also spurious alarms for faults that do not actually exist. Before we go on to the third step, I'm just going to go back to Dave to go over the questions that we've been asked.
One is, does this theory apply to an ATS? Yes, our 8660 Mark II module carries out the same synchronization process and transfer as 28610 Mark IIs do, only with the mains.
Yeah, I'd just like to add further to that as well, actually, because it is a very good question. So a lot of the steps that we're going through now are applicable to an ATS. Yes, the governor and AVR we've just gone through, they technically aren't applicable to one of our ATS units. But if we're talking about synchronizing and load sharing application with the mains, if the DeepSea generator controller has bad control over the governor and AVR, that is going to affect your mains parallel, because at the end of the day, for the generators to synchronize with the mains, it has to have good control over the governor and AVR. When that generator goes in parallel with the mains, for that generator to control kilowatts and kVARs, it has to have good control over the governor and AVR. So whilst these steps are not specifically, or step number 1 is not specifically for an ATS controller, it does indirectly affect ATS controllers as well. Actually, step number 2, number 3, and number 4, number 2 we've just done, they are directly related to ATS controllers. At the end of the day, this is a generic synchronizing and load sharing setup, commissioning, and fault finding procedure, which can be used with all DeepSea products. I've just seen now someone's asked the question, can a 1 amp CT secondary be used with DSE controllers rather than a 5 amp CT secondary? The answer is yes. Most of our high-end controllers, really 6000 series and up, support 5 amp secondary support 1 amp secondary CTs. There are pros and cons for using 1 amp over 5 amp and 5 amp over 1 amp, but unfortunately we do not have time to go over those during this course. But yes, with our synchronizing and load sharing controllers, it is perfectly possible to use a 1 amp CT if you wish. We've had another question come in saying, what is the AVR max trim and how to solve it? I'm not sure what this is relating to, but I'm going to have a guess of maybe it is the alarm AVR trim limit. If you have ever seen the alarm AVR trim limit, then this suggests that actually your switch 2 value and switch 1 value have not been set up correctly. Effectively, what AVR trim limit alarm means, if it has been enabled in your controller, is that the DeepSea module is trying to request the AVR to do more work, but unfortunately, it cannot. This might be because the AVR switch 1, switch 2 have not been set up correctly, so the DeepSea module does not have a good enough range of control, for example, plus or minus 10% of nominal voltage. Or it could even be that you're requesting the generator to do something and it physically isn't possible. So this might be, for example, asking a 100 kVA generator to produce 200 kVARs. That's far too much for that generator to produce. So when the DeepSea module tries to request the AVR to do that, the AVR physically doesn't have enough power to be able to ask the generator to do that, and therefore gives you AVR trim limits.
One question's been, is there a possibility of the set going unstable when the breaker is first closed? Yes, there is, but your trip levels still apply.
And if the generator goes unstable when the generator breaker is closed, that would actually suggest that you do have a problem with the PID, gain and stability settings on that governor or AVR, depending on where the generator goes unstable. And we've had one last question come in saying, the power system is Delta 3-phase 3-wire. Do we need to remove the neutral connection in the controller? Well, if it is a true 3-phase 3-wire Delta system, there is no neutral coming from your generator. Therefore, you do not connect it. The DeepSea module does not need a neutral connection to work. So if you have a 3-phase 3-wire Delta system, which natively does not have a neutral, you do not connect anything to the neutral terminal.
There are people still asking about videos. If you'd like to email into support@deepseaelectronics.com, we'll be able to provide you with any information that you need from there.
Okay, we'll carry on with the presentation now then. We'll go to step number 3. So step number 3 is checking the communications between the two devices, or between multiple modules. And by communication, we're actually referring to the MSC link. MSC, by the way, stands for Multi-Set Communications Link. So what you first need to do, you need to connect your DSE module to a PC with the DSE configuration suite software installed. Then you would go to the SCADA section of the DSE configuration suite, and you go to SCADA, generator, and multi-set. And then what you just simply need to do is check that the numbers on screen match the numbers of controllers you have. So sets on the bus relates to how many 8610s do you have connected on the MSC link, and mains controllers on the bus refers to how many 8660 or 8680 controllers you have connected on the bus. Simply, if the numbers don't match up, there's a fault on the MSC link. Now that fault could be anything to do with cabling, incorrect termination, etc. But the easiest way to find out which controller has the fault is to go into each controller individually and look for whichever one is reporting 1 on the numbers. Because if it's only seeing itself, that means the MSC link is not working. One thing to remember though is what many people do to test the MSC link is they remove the wire from the back of the DeepSea module and then reapply it to see if the alarm appears and then disappears. One thing to remember, the DeepSea module will only give you an MSC failure alarm if the module's MSC link was working before and then has failed. So for example, if you were to turn on a DeepSea module with no MSC link connected, you would not see an MSC failure alarm. That is because there was no working MSC when the module powered up. So just keep in mind that the MSC failure alarm only appears when there was a working MSC link and then it disappears. So let's just do a bit of housekeeping and talk about what could cause MSC failures. The most common MSC failures we find is people using the incorrect type of cable. Now the cable you should be using for MSC communication is CAN bus rated cable. Now the cable we recommend is from a manufacturer known as Belden, and its part number is 9841. Now this cable has a very special characteristic, which is a 120 ohm impedance, and again suitable for CAN bus communication. The cable we also advise should be shielded or screened and shielded. In theory, any CAN bus rated cable will work with DeepC, but we always recommend Belden 9841 because it's the cable we use here at DeepC for testing, and we know it works. We believe also it's some of the best cable you can buy. But in theory, as long as you have purchased CAN bus rated cable, it should work fine. The next most common problem we come across is wiring of the MSC link. On the board here, you can now see how the MSC link should be wired. You can see it's wired in what we call a daisy chain type arrangement, where we have wires going into the module and out of the module, into the module, out of the module. You can also see there is a 120 ohm termination resistor at the start of the cable and the end of the cable. It is very important that you wire the MSC link in a daisy chain configuration like shown here, and that you also put in a 120 ohm termination resistor at the start and end of the cable. If you forget to put the termination resistors in, this can lead to MSC failures. If you use the wrong type of cable, this can lead to MSC failures. And if you do not wire in a daisy chain connection, but instead this type of connection, this will also lead to MSC failures. The difference between this type of wiring and the previous wiring is that it's not daisy chained. We only have one set of cables in the terminals. This will lead to MSC failures, so we advise strongly against what we call spur type wiring, which is what is shown on the board now. So going through, what could be the problems if we don't do this test? Well, if you remember earlier, I did say that the MSC link is used to tell each generator how much power to produce. If the MSC link is not working, the DeepC modules won't know how much power each generator should produce, and therefore your load sharing will be very, very unstable. It actually will be completely uncontrolled. Worse yet, the MSC link also offers lots of protections to help prevent against out-of-sync closures due to things like bus sensing failures. So without having the MSC link, you will eventually encounter out-of-sync closures. So it's very important that you make sure you have a working MSC link. Just looking at one of the questions that's just come in, and it says, what happens if the MSC link fails? For example, the wire is cut. Well, if you only use one MSC link, and I'll come back to what I mean by that in just a short second, then the modules will no longer communicate. And as you can see here, you potentially may have out-of-sync closures, or no load sharing will work whatsoever. You could end up having reverse power trips, loss of excitation trips, lots of problems. But this is not necessarily now a problem with the 8610 Mark II controllers. The advantage with using the 86 Mark II controllers is that you can actually wire two MSC links. So that means then if the first MSC link fails, the modules automatically revert to the second MSC link, effectively giving you MSC redundancy. But on top of that, we also have a feature whereby if the MSC link completely fails, so for example, MSC1 and MSC2 fails, you can actually revert to a droop form of load sharing. Droop form of load sharing basically means that the modules will carry on load sharing. However, the frequency and voltage will not be maintained at nominal, but that is just a function of droop. So at least there are redundancies built into the DeepC module if you choose to enable them and wire them in case of MSC failures. Another question has just come in, so we have to connect two 120 ohm resistors even if we only have two gensets. That is correct. If you have two gensets, 5 gensets, 32 gensets, it does not matter. you must have a 120 ohm termination resistor at the start of the MSC cable and at the end of the MSC cable. If you only have one generator on its own, you can leave the MSC terminals completely disconnected. Okay, we'll carry on now with the final part of the presentation, which is going through step number 4. Step number 4, this is basically doing synchronizing checks across generator breakers to make sure nothing has been wired incorrectly. So the way we're going to do this test, we're going to start a generator and close its breaker, making the generator bus live. We then start a second generator and we do not close the generator breaker. And that's very important because all the way through this procedure so far, our generators have not been placed in parallel. Every step we've done so far has been done on each generator in turn in isolation. We then navigate to the synchroscope on the DeepSea module's display, which you can see even if the DeepSea module has not been requested to synchronize. And then we measure across the open generator breaker for L1, L2, and L3. And when the synchroscope shows the phase dot in the middle, you should be seeing roughly 0 volts across the open breaker. Problems could be that if 2 phases have been swapped over for any reason, the DeepSea module's display would show them in sync, but actually, when you measure across the breaker, you will see that they aren't in sync. Now, many people would assume that the DeepSea module's inbuilt phase rotation protection would protect against this. However, that is not always the case, as we will see in the next slides. So here is an example of a correctly wired breaker. So in this case, you can see that on the left-hand side here, the DeepSea module is measuring L1, L2, L3. At the breaker, it's L1, L2, L3. And at the other side, it's L1, L2, L3. And when the DeepSea module synchroscope is showing the 2 supplies in sync, we are seeing 0 volts across the open breaker. Perfect. Everything is okay. However, if the following mistake was made, where for some reason the wires were swapped here between the DeepSea module sensing and the breaker, then unfortunately the DeepSea module would not detect this problem until it is too late. As you can see here on the left-hand side, the DeepSea module is measuring L1, L2, L3. On the right-hand side, it's measuring L1, L2, L3, and it's measuring 0 volts between them. But because somebody has crossed the generator phase wires to the breaker, actually we have 230 volts across this breaker here, which the DeepSea module does not detect because the fault has happened after the generator sensing. So in this case, the DeepSea module is sensing 0 volts. Therefore, it is showing on the display, everything is okay, everything is in sync. And then across the open breaker, you would actually see 230 volts. At this point, the DeepSea module would request the breaker to close and everything would end badly. Some people say that they don't have to do these checks because they wire directly on the breaker themselves, on the lugs of the breaker. So it's much more safe and secure. Unfortunately, that is not always true because if you have a cross here and also have a cross on the sensing wires, you could come across the same problem. So regardless of how you wire your sensing on the breakers further downstream, it does not matter. You should always do this phase rotation check across the breaker using a multimeter across the open breaker, doing L1, L2, and L3. If you do not do this check, what could happen? Well, you can clearly see that it could end up the generator closing out of sync. If a generator closes out of sync, unfortunately, it goes bang. So it's very, very important that you do these phase rotation checks. But if we just go back and remember, you'll see that for step number 1, step number 2, and step number 3, if you did not perform those tests, they all had a very common fault, which was unstable, incorrect, unworking load sharing. So lots and lots of times people will call us at DeepSea and say, I have a generator system where the load sharing is unstable. What could be the problem? Well, as you can now see, the problem could be something with your governor or AVR. It could be something with the CTs. It could be something with the MSC link. So the 4 steps to synchronizing is not just a commissioning procedure, it is also your fault finding procedure. So whenever you have any form of load sharing issue or synchronizing issue, the first thing that we would advise you do at DeepSea is do these 4 steps to synchronizing. I would say 95% of the time, if you do the DSE 4 steps to synchronizing, you will find your problem. And by finding the problem and doing the 4 steps, in most cases, you will also fix the problem. The other advantage of the DSE 4 steps to synchronizing is you're not necessarily just testing the DeepSea module and its calibration. You're also testing the generator as a whole. So going back to the first procedure, which was setting switch 1 and switch 2, and making sure we could increase and decrease generator voltage and frequency. If you remember, I said the reason why we choose 52.5 Hertz as one of the tests is that we can prove then that the generator, in theory, can produce full power at 50 Hertz because it has a very similar actuator position as 52 Hertz with 52.5 Hertz with no load. So we've once had a customer who was doing the 4 steps and he was trying to drive to 52.5 Hertz and unfortunately couldn't make it. Under further investigation, they actually found they had an issue with their fuel pump. And by doing the 4 steps, they proved the reason why they were having load sharing issues actually wasn't anything to do with the DeepSea module at all. It was a fault with the engine. Now, I can imagine that for some of you, these 4 steps, there's quite a lot to remember. So the question then becomes, well, how do you remember? It's quite easy, really, referring to the product's operator's manual. Everything we've gone through today is actually written down in the module's operator's manual, step by step. And a lot of the information and diagrams I have used in today's presentation have actually been taken from the operator's manual. So we would always advise whenever doing any form of synchronizing and load sharing that you do have a copy of the product's operator's manual, because in the commissioning section of that operator's manual, you will find these 4 steps written down. So just to conclude today's training seminar, the 4 steps of synchronizing, which we've gone through today, they're used as both your commissioning and fault finding procedure. You will see all the time at DeepSea, if you phone us for technical advice, we will ask you to do these 4 steps because in most cases, you will find them. You will find the problem by doing them. There is a written procedure for the 4 steps included in the commissioning section of the module's operator's manual. All operators manuals are actually included as a part of the DSE configuration suite software under the help menu. So as I mentioned earlier, as you need the laptop to do the switch 1 and switch 2 settings, you'll already have the written down procedure because it's included in the operator's manual, which is also included in the software under the help menu. Any unstable synchronizing or load sharing issues could be caused by problems with your governor, AVR, current transformers, or MSC link. By doing the 4 steps, you will actually isolate where these issues are lying. In addition to isolating where these issues lie, potentially with the wiring or configuration with the DeepSea module, the 4 steps will also help you identify any potential external faults as well. And again, just to reiterate it again, we strongly advise that you always perform the DSE 4 steps of synchronizing as a first step in commissioning or fault finding. Because in most cases, by doing these 4 steps, you will find your problems and you will resolve them. Obviously, if you've gone through the 4 steps and you are still having issues, by all means, please feel free to contact us at technical support. That's what we're here for. So that concludes our training today. I'd just like to open up the Q&A section again for any more questions coming in. So please feel free. If anybody doesn't have any questions, and I'd like to thank you for participating again today. We will be soon putting some more training seminars online. So please keep your eyes open for those. We will be advertising them both on LinkedIn and via emails being sent out. So if you are registered on our website, please make sure you do accept any form of marketing information coming from us, because we will be releasing more training courses that way. So again, if anybody has any further questions they would like to ask about anything that's been covered today, please feel free to put them in the question and answer section. If not, what I will do, I will leave my laptop and the presentation going for another 10 minutes. If anybody has any questions they would like to ask, please feel free. I can see one question's come in. Yes, the recording will be available to re-watch. If you would like a copy of the recording, please do send an email through to our technical support department. The email address is just simply support@deepseaelectronics.com, requesting the presentation, and we can send you a live recording of that to re-watch at your leisure whenever you wish. Okay, so I'd just like to say goodbye from myself. Again, I'm going to leave the presentation open now for the next 10 minutes. If anybody wants to still ask some questions, please feel free and I'll come back in 10 minutes time. Dave?
We've got one question indicating what happens if I have a different switch 2 value when driving up and down. Simply choose the center value. It'll be absolutely fine. Do I need a load sharing module when using an ECU and load sharing with dissimilar sets? If you have one set that is a conventional diesel and one set that is has an engine ECU, they will load share together, but they both need load sharing modules.
Okay, I'm going to leave the presentation here for 5 minutes. Please feel free to ask any other questions and I'll come back to those after I've had a quick break. Again, thank you all for attending. Hello, I've come back. Okay, so I can see a couple of questions have come in. So the first question I can see here is just a, kind of, I guess, a general question in terms of DeepSea modules. Is it okay for the DeepSea module to control breakers using its DC outputs rather than the volt-free outputs? Yes, that's perfectly acceptable, but just keep in mind that if you're going to be using the DeepSea module's DC outputs, they're only rated to 2 amps DC. So really, you would have to use the DC output to drive a volt-free contact, such as a relay, and then use that to then drive your switchgear. So there's nothing wrong with using the DC outputs, just that we would always advise using an external slave relay because they're only rated at 2 amps. I can see another question's come in again relating back to current transformers. So I'll just do a quick rundown of current transformers before we end the session today. So current transformers come in 2 variants, a 1 amp secondary and a 5 amp secondary. Each has its own pros and cons. Normally, where possible, we would always advise using a 5 amp secondary. The reason for this is a 5 amp secondary has a much higher precision. For example, if you had a 100 to 1 amp CT, you've only got 0 to 1 amps to reference 100 amps. Whereas if you were using a 100 to 5 amp CT, you have 0 to 5 amps to reference the same 100 amps. Effectively, you're getting 5 times the precision, making your reading far more accurate. So normally, it is always better to use a 5 amp CT because the reading you will get from a 5 amp CT is normally more precise. Though there are downsides to using 5 amp CTs. Because you could potentially be outputting 5 amps from a 5 amp CT, this does mean that the VA rating of your CT will have to be much higher for 5 amps. In what we mean by VA rating is the power output of that CT. And the VA rating of a CT has to be larger than the VA consumption of a DeepSea module, which is 0.5 VA, and the VA consumption of the cables you are using in between the DeepSea module and the CTs. Normally, the larger the diameter of the cable, the smaller the VA burden that cable has. The VA burden of a cable increases with cable length. So a 1 millimeter square cable running 1 meter will have a larger VA burden than a 2.5 millimeter square cable running the same distance. So if your CTs are a long distance away from the DeepSea module, that would mean your cables potentially will have a very high VA consumption rating, which then means you would have to purchase a 5 amp CT with a very high VA output to accommodate for that. The next thing to keep in mind with VA ratings of a CT, normally when you purchase a CT, it doesn't have one VA rating. It actually has numerous VA ratings for different accuracies. So for example, for 1% accurate, it may only have a VA rating of 3. But for 2% accurate, it may have a VA rating of 6. For 5% accurate, it may have a VA rating of 12, for example. So when you purchase a CT, you first need to make sure that the VA rating of the DeepSea module, the VA rating of the CT is high enough at the accuracy class you require. And because 5 amps will consume a higher VA, normally what most people will do for long cable distances, they will use a 1 amp CT instead, because 1 amp over the same cable will consume less VA, and therefore you can get away with having a lower VA rated CT. So in a nutshell, to kind of summarize, 1 amp CTs have a benefit of normally you can run them over longer cable distances for the same VA rating, but you sacrifice precision and accuracy on the reading because you only have 1 amp of scale. On the flip side of that, 5 amp CTs have 5 amps of scale, so you have a much better precision and accuracy, but you have a lot less cable run you can do for the same VA. I hope that answers your question. Another question's just come in actually about 86 Mark 1s and Mark 2s. And in reference to something called MSC compatibility. MSC compatibility does not need to be enabled when you're going from any version of Mark 1 86 to any version of Mark 2 86. However, you do need to enable MSC compatibility if you are using an 86 Mark 1 or Mark 2 with the older 75 and 5500 series products. So the MSC compatibility is only to make the 86 Mark 1 and Mark 2 work with the DSE 55 and 7500 series products. So before I finish the presentation for today, do we have any last minute questions? Okay, I can see that no other questions have come through. So again, I'd just like to thank everyone for attending. And again, please keep your eyes open on LinkedIn, on our website, and via email for information on upcoming courses. Again, we do send emails out to everyone who is registered on our website. So if you are registered on the website, please make sure you are a part of our mailing list for upcoming training courses. Again, thank you from myself, Ash, and thank you from Dave.
Thank you very much.
And we look forward to seeing you again on our courses in the future. Thank you very much.